Good morning, dear children. Welcome back to the lecture of chemistry. Today we are going to revise coordination compounds. Now, a chemical bond consists of covalent bond. A covalent bond is formed between two non-metals by sharing of mutual sharing of electrons. Ionic bond is formed between a metal and non-metal, and there is electrostatic force of attraction between them. A coordinate bond is formed by sharing lone pair of electrons. So example of covalent bond is HCl, ionic NaCl, and that of coordinate is ammonium ion. Now let us study the coordinate bond. Now in coordinate bond, Lewis acid and Lewis base, they react to form coordinate bond. Lewis base is electron donor while Lewis acid is electron acceptor. The example is ammonium ion. Transition metal atoms or ion form a large number of compounds in which ions or neutral groups are bounded to metal atom or ion through coordinate covalent bonds. Such compounds are called as coordination compounds. Now, addition compounds are further classified into double salt and coordination compounds. Now, double salts, they lose their identity, while coordination compound, they retain their identity. The addition compounds, which are stable in solid state only but broken into individual compounds when they are dissolved in water, are called as double salt. Double salt are also called as lattice compounds. Then double salts, they are generally ionic. They have normal valency, while that of complex salt, they may or may not be ionic, but the complex part definitely involve coordinate bond, and they have primary and secondary valencies. They are in solid state, both of them, for double salt as well as coordination compounds. Example of coordination compounds used in our daily life: vitamin B12, hemoglobin, and chlorophyll, which is present in plants. Now, Sir Alfred Werner, he has given Werner's theory. It is based on the following postulates. Metal possesses two types of linkage, that is valency, primary valency and secondary valency. Primary valency is ionizable, while that of secondary is non-ionizable. Primary valency is number of ionic bond, that means it deals with oxidation state. Secondary valency is equal to number of coordinate bond, that refers to coordination number. Now different compounds, they have different number of ions in solution. Primary valency of a metal can vary, but secondary valency always remains same. Every metal has tendency to satisfy its primary and secondary valency. Here are the example of primary and secondary valency. Silver chloride, where silver is a metal, chloride is a non-metal. Iron sulfate, sodium chloride, negatively charged is chloride, neutral is ammonia, and positively charged NO. nitrous oxide. Based on ionizability complex, they exhibit various color like yellow, purple, green, and violet. Now the important terms in coordination compounds. Now there are few important terms like ligand, central metal ion, coordination pair, charge on complex ion, coordination number, counter ion ionization pair. The central atoms are also referred to as Lewis acid. Now, in coordination entity, the atom or ion to which a fixed number of ion or group are bounded in definite geometrical arrangement around it is called as central atom or ion. Classification of ligands. Now, what is ligand? Ligands are electron pair donors. A molecule or ion which is coordinated to the metal atom or ion in a coordination compound. Classification of ligands. Ligands are classified based on the denticity. Ligands are charged positively and negatively, and they are neutral also. Negatively charged ligands are classified into monodent and polydent. Neutral are also further classified into monodented and polydent. Now here are the example of monodented negative ligands. Cyanide, fluorine, chlorine, bromine, iodine, hydrogen, nitrate group, nitrito group, nitrato group, hydroxo group, amido group. Bidentate oxalate ion, acetyl acetonate, then glycinate. Ethylene diamine triacetate ion and EDTA. Neutral ligands: amine, aqua, nitrosyl, carbonyl, thiocarbonyl, phosphine, triphenylphosphine, thiourea. So these are tridentate, bidentate and polydentate ligands. Now ambidentate ligands. Here in both the example, you can see the difference. In first example, nitrogen is a donor atom, while in second example, oxygen is the donor atom in NO2. Now, what is this ambidentate ligand? A ligand which contains two donor atoms, but only one of them forms a coordinate bond at a time with central metal ion. So here are different example. Nitrito, nitrogen is the donor. In second example, oxygen is the donor. Then thiocyanato, S is the donor. Isothiocyanato, N is the donor. Cyano, C is the donor. Isocyano, N is the donor. Now, when bidentate or polydentate ligand uses two or more of a donor atom to bind a single metal ion, then a ring-like structure is obtained, and it is known as chelate, and the ligand is known as chelating ligand. A hexadentate ligand example is EDTA. Coordination number, number of electron pairs accepted by central metal atom or ion is known as coordination number. Now here in this example, the coordination number of Pt and Ni, that is platinum and nickel, is 6 and 4 respectively. Now, homoleptic and heteroleptic complexes. Complexes in which metal is bounded to only one kind of donor group is called as homoleptic. Complexes in which metal is bounded to more than one kind of donor group is called as heteroleptic. Now, complex ion. What is this complex ion? A complex ion, it is electrically charged radical which is formed by combination of simple cation with one or more neutral molecules or one or more simple anion or in some cases positive groups. So here you can see this is a simple ion and this is a complex ion. Here the coordination number will be 2. In this example, the coordination number will be 6. Now, what is EAN? That is effective atomic number. It is the total number of electrons present in the metal atom or ion after gaining electrons from the donor atom of the ligand. En is equal to Z, that is atomic number, minus number of electron lost in the formation plus number of electrons gained from the donor atom of ligand. Or you can also say that EAN is equal to atomic number minus oxidation number of metal plus 2 into number of donor atom. This is the formula. Now, nomenclature, IUPAC name. There are few rules for the nomenclature. Now, let us see what are those rules. The cation is named before the anion. Metal forms cation and non-metal form anion. While naming a complex, ligands are named first in alphabetical order in case of multiple ligand. Here you can see K4, it is a cationic part because potassium is a metal, and CN, it is an ionic part because it is a non-metal. The name of an ionic ligand end with suffix O. So IDE suffix change to O. If it is ATE, it changes to ATO. If it is ITE, it changes to ITO. Neutral ligands are referred to the usual name for the molecule, like ethylene diamine. If it is water, it is called as aqua, ammonia amine, and carbon monoxide is carbonyl. Greek prefixes are used to indicate the number of each type of ligand when present more than one time in the complex. Di means 2, tri means 3, tetra means 4, penta means 5, and hexa means 6. So now rule number 3. While naming a complex, if a complex is anionic, the central metal atom or ion name end with ATE. Then coordination number 2, 3, 4, 5 and 6. Coordination number 2, it shows linear geometry. Coordination number 3, it shows trigonal, planar. Coordination number 4, tetrahedral and square, planar. Coordination number 5, square, pyramidal. Trigonal, bipyramidal. Coordination number 6, geometry will be octahedral. Now, isomerism of coordination compounds. Isomerism, it is the phenomenon in which the compounds have same molecular formula but different physical and chemical properties. Now, ionic bonds are non-directional, so the compound, they do not exhibit isomerism. Coordinate bonds are directional, So coordinate compound they have or they show isomerism. Isomerism is classified into structural isomerism and stereoisomerism. Structural isomerism consists of ionization isomerism, solvate or hydrate isomerism, linkage isomerism, coordination isomerism. Stereoisomerism consists of geometrical isomerism and optical isomerism. Ionization isomers, compound which give different ions in solution even they have same composition, are called ionization isomers. BSO4, it is having white PPT. AgNO3, when it is added to this solution, it gives AgBr, which is a pale yellow PPT. So these are the examples. Solvate isomerism or hydrate isomerism. They have same molecular formula but differ in the number of water molecule inside and outside the coordination sphere. In this, anions are exchanged with respect to water molecules. Linkage isomerism. It arises in coordination compound containing ambidentate ligand. Linkage isomers have same molecular formula but differ in linkage of ligand to the central metal atom. So here are the examples. Geometrical isomerism. Depending on the spatial arrangement of ligand about the central metal atom, it consists of cis and trans. Cis means same and trans means different. Here are the examples: cis but2in and trans but2in. So orientation of atom or group of atom around or about the double bond. Now, if the coordination number is 4, it shows square planar and tetrahedral geometry. If it is 6, it shows octahedral geometry. Here are the examples of cis and trans. Complex having coordination number 6 shows octahedral geometry. It shows cis and trans isomers in both the examples. Complex having coordination number 6. Optical isomerism. They are also called as enantiomers. Isomers which rotate the plane of polarized light are called as optical isomers. The optical isomers are mirror images and non-superimposable. They are called as enantiomers. And a molecule or ion that exits a pair of enantiomer is said to be optically active and exhibit optical isomerism. Stereoisomers, they are mirror images. Mirror image of left hand is identical to that of the right hand. Levo means it rotates to the left and dextro means it rotates to the right side. So these are the optical isomers. Now let us understand the valence bond theory. To satisfy primary valency, central metal atom tend to lose required number of electrons and creates vacant orbital. These vacant orbital undergo hybridization and gives desired shape to the complex. Now there are different type of hybridization: sp, sp3, dsp2, d2, sp3. In sp type of hybridization. The geometry is linear. In sp3 it is tetrahedral. In dsp2 it is square planar, and in d2sp3 it is octahedral. And in sp3d2 it is octahedral. Now, if n minus 1 d orbital is involved in hybridization, the complex are inner orbital or low spin or strong field ligand complex. In presence of strong ligand, electrons are regrouped against to the Hund's rule. If nd orbital involved in hybridization, the complexes are called outer orbital or high spin complexes. In the presence of weak ligand, electrons are not regrouped according to the Hund's rule. Paramagnetic nature is due to the presence of unpaired electrons. Now let us take an example of CONH3 6. The geometry of the complex can be known by the knowledge of hybridization. The cobalt ion is in +3 oxidation state and has electronic configuration 3d6. And the hybridization is D2sp3. Six pair of electrons, one from each ammonia molecule, occupy the 6 hybrid orbital, and it is inner orbital complex. So 6 pair of electrons from 6 ammonia molecules. Thus the complex has octahedral geometry. It is diamagnetic due to the absence of unpaired electron in the formation of this complex. Since the inner d orbital 3d is used in hybridization, the complex is called as inner orbital complex. The paramagnetic octahedral complex COF6 uses outer orbital 4d in hybridization. Now, what are the limitations of valence bond theory? It could not explain the color given by complex in aqueous solution. It could not explain the magnetic data of the complex. It could not account for spectrochemical series. It does not give quantitative interpretation of thermodynamic or kinetic stability of coordination compound. It does not distinguish between strong and weak. Let us understand crystal field theory CFT. Now in crystal field theory, the electron pair on ligands are viewed as point negative charge that interact with d orbital on the central metal. The nature of the ligand and tendency toward covalent bonding is ignored. You can see here the d orbitals. Ligands viewed as point charges at the corners of an octahedron affect the various d orbital differently. You can see in the figure that there is strong repulsion and there is weak repulsion. Crystal field splitting in octahedral coordination entities, the repulsion between ligand, one lone pair and d orbital on the central metal result in splitting of energy of d orbital. You can see it in the picture. Now this is a diagram which shows d orbitals in free ion, average energy of orbital in spherical crystal field, then crystal field splitting energy. Down it is T2G, the difference is 2 by 5 delta 0, and at the top it is EG 3 by 5 delta 0. So dx square minus y square and dz square is in Eg, and dyz, dxz, dxy are in T2G. Crystal field splitting in tetrahedral coordination entities. In tetrahedral coordination entity formation, d orbital splitting is inverted and is smaller as compared to the octahedral field splitting. Here you can see the diagram T2G and EG. So spherical environment and in tetrahedral crystal field. The energy difference between the two sets is called as crystal field splitting in tetrahedral field, and it is abbreviated as delta T. It has been observed that splitting in tetrahedral complex delta T is less than that in octahedral complex delta 0. So it has been found that delta T is equivalent to 4 by 9 delta 0. The magnitude of crystal field splitting delta 0 depends on the field produced by the ligand and charge on the metal ion. Some ligands are able to produce strong field, in which case the splitting will be large, whereas others produce weak field and consequently result in small splitting of d orbital. Now, strong field ligands or low spin complex, weak field of ligands high spin complex. Strong field ligand forms low spin complex and weak field ligands form high spin complex. Now, limitation of crystal field theory. Now, consider ligand as a point charge dipole only. Does not take into account overlap of ligand and metal orbital. It does not take into account of the covalent character of bonding between the ligand and the central atom. It failed to explain strength of ligands. Example, fails to explain why CO is stronger ligand than Cn minus in complex having metal in low oxidation state. Stability of the complex. Now, stability of complex in solution refers to the degree of association between two species involved in state of equilibrium. So, overall stability constant is written as m plus 4l, that gives ml4. Beta 4 is equal to ml4 upon m into l raised to 4. Important application of coordination compound. Now, coordination compound find use in qualitative and quantitative chemical analysis. Familiar color reaction given by metal ion with number of ligands as a result of formation of coordination entity. It forms the basis for their direction and estimation by classical and instrumental method of analysis. Example of such reagent include EDTA, DMG, alpha nitroso, beta naphthol, cupron, etc. Hardness of water is estimated by simple titration with Na2-EDTA. Calcium and magnesium ion, they form stable complex with EDTA. So selective estimation of ion can be done due to difference in stability constant of calcium and magnesium complexes. Some important extraction process of metal like those of silver, gold make use of complex formation. Gold combined with cyanide in presence of oxygen and water to form coordination entity. In AuCN2 in aqueous solution, gold can be separated in metallic form from this solution by addition of zinc.